Let's welcome Professor.
Thank you. Thank you. It's Thank you. It's a great pleasure to be here. I thank the organizer for the invitations. So what I'm going to talk about today is about non-parametric and functional regression estimators based on orthogonal systems. Maybe a better title for my speech is my talk is uh, applied harmonic analysis meet machine learning, because what we're going to see is how to use tools from harmonic analysis to apply for machine learning problems, essentially non-parametric regression and linear functional regressions, and essentially to prove why the given estimators are are good. Okay, so we're going to talk about curse of dimensionality, what Richard has mentioned, and also the optimal order of convergence, donc of the estimators. So the first part is just mathematical preliminaries. Please interrupt me if you have any questions. So also the second part is about the multivariate random projection based NP regression estimators, numerical stability of the estimator, and order convergence rate. The third part is truncated kernel ridge regression estimators. It is about dimension reduction. And the last part is about random projection based linear functional regression estimators. For functional regression estimators, this is very interesting because we are not dealing with samples of random variables. We're dealing with stochastics process, and this is very interesting in such a way that one can handle large data by using the functional regressions estimators. So we'll see donc how is. So we consider the classical regression, non-parametric regression problem. We have the response yi equals fxi plus epsilon I, where the xi are IAD random vectors and the epsilon I are standard random vectors, the noise with variance sigma square. They are independent from the xi. The xi has to be thought as random samples. There exists a variety of non-parametric regression estimators for solving problems, such as Marzan-Rosenfeld kernel-based estimators, the kernel-ridge regression estimators, and the random projection-based estimators. And there's other kind of estimators. Well, we are interested in the third class of estimators, as well as the truncated kernel-ridge regression estimators. You'll see that why we are interested on the truncated kernel regression estimators. The kernel regression estimators have the advantage to be fast, but require a very high load of computations. So we have to use a truncated version of these estimators. So the usual way to construct an estimator is to solve for minimization problems. F hat, the estimators, arg over a functional space H of 1 over n, the sum from 1 to n of L fx ayi. L is the loss functions. One of the most used loss function is the Tikhonov regularized loss functions. So the issue is how to choose the regularization parameter lambda, and why we need the regularization parameter lambda. Well, the previous NP model suffers from the curse of dimensionality. For large or even moderate values of dimension d, the computational load required by an NP means non-parametric regression estimator, grows fast or even in exponential way with the dimension d, and its convergence rate slowly drastically. This is what Richard said. Well, we do have an excellent theoretical result about any estimator that use least squares to solve problem 2. Actually, this is a result by Stone, published in 1982, and it says that the optimal convergence rate of any NP least squares estimated for solving 2 is of order n of the power minus 2p over 2p plus d. What's the p? The p is the the function f, the regression function f, has to be of class Cp with base derivative being order continuous. So we assume a kind of strong condition on the regression function. And even with this strong condition, we got only the best order of convergence is of order n of the power minus 2 over 2p plus d. It's an excellent result, theoretical result. Why? Because this gives us if your actually estimator is good or not, if it attains the optimal convergence rate. And this is the optimal convergence rate. This is proved theoretically. And this is very, very important result of Stone. So the issue now, if you are going to develop the design an estimator, you have to look for the convergence rate. And if your convergence rate is of this type, exactly of order n minus 2 over 2p plus d, you have the best or a good estimator. This is the issue. And this is what we're going to do. Because if you, well, we have developed an estimator. We submitted this work to a journal. The first question is it a good estimator? Does it converge fast? So if you are able to prove this convergence rate, you won. Well, what we are going to, actually, my background and my research, primary research area is applied harmonic analysis approximation theory, not mathematical statistics. So what I have done the last 5 years, I have applied harmonic analysis tools to solve problems from machine learning and mathematical statistics. And it's interesting how to use these tools, I mean, in this interesting area of machine learning. So what we are going to use, the orthogonal systems. Orthogonal systems generated, for example, by Jacobi polynomials. Jacobi polynomials are orthogonal polynomials with weight function W alpha beta. It's just 1 minus x to the power alpha, 1 plus x to the power beta, and they are orthogonal over L2 minus 1, 1 with the weight, these weight functions. And what about the Jacobi polynomials? If alpha equals beta, the maximum is attained at either 1 or minus 1, and is of order k of the power alpha plus 1/2. K is the degree of the Jacobi polynomials. Well, about interesting also result, because we're going to use some result about the spectral behavior of random matrices, gram random matrices or kernel random matrices. So it's important to get an idea about the eigenvalues, the behavior of the eigenvalues. And there is a well-known Chernoff, matrix Chernoff theorem that provides us with an estimate of these eigenvalues. So what says this, the matrix Chernoff theorem? If you consider a sequence of n independent d by d random Hermitian matrices, assume that for some L, the zk is positive and less than L times identity of the order d. What does it mean? It means that the eigenvalues of zk are positive, and Lid minus zk is positive, semi-definite. So if we take the minimum eigenvalue of the expectation of A is a random matrix, and mu max is the maximum value of expectation of A. If we take the expectation of A, we have a deterministic matrix, no longer random matrix. So the probability that lambda mean the minimum value of A less than 1 minus delta mu me less or equal to d exponential minus delta square mu mean over 2A. And similar inequality holds for the maximum eigenvalues. This is interesting theorem about behavior of random eigenvalues of random matrices. Another tool is Gershgorin circle theorem, and this is what says Gershgorin circle theorem means that if we take a complex matrix, a square matrix, then every eigenvalues of A lies in a disk with center the ith diagonal of A and with radius the sum of the coefficient, absolute value of the coefficient outside the diagonal. This is interesting also too. So there is a whole set of results from linear algebra and behavior of random matrix eigenvalues of eigenvalues that we have going to use. So also for to construct our non-parametric regression estimators, multivariate non-parametric regression estimators by projection over polynomial spaces. So there is many kinds of multivariate polynomial spaces. One of the well-known multivariate spaces is totally degree multivariate polynomial spaces. This one is, well, actually has the drawback that its dimension is so big. Its dimension is n of the power d over d factorial. So a better multivariate dimensional spaces, polynomial dimensional space is hyperbolic cross space of degree n. And what's the difference is that if you sum up the qth norm of yes of the xi of the indices is later equal to n. So this is the hypercross space of degree n. So this is better, has much lower dimension. The problem that there does not exist any result that gives you the dimension of this space. Well, the last dimension is that multivariate spanned by multivariate Jacobi polynomials is this one. This is what we are going to use. Donc, and we know what its dimension. Well, we are combining the use of this space with the ANOVA decomposed structure of a function of with multivariate functions. That's the ANOVA decomposition. And what's interesting is that we know the dimension of our space on which we are going to project is of order n of the power m times d of the power n. So for m, say small m, it's okay as dimension. So it's what we're going to do is dimension reduction of the problem by choosing an appropriate polynomial space on which we are going to project our regression function. Is it okay? Do you have questions? So, and what we are going to do is that we are to construct our basis functions. So our basis functions are constructed from the multivariate Jacobi polynomials. And this one, that's our basis for projections. And, well, we can write our multivariate polynomial space, subspace, in this form. And we can order our basis function by this way. This is an order of basis functions. They form orthonormal basis also of our projective subspace. And then we go back to our regression problem. So we are going to find the solution of this minimization problem. Well, if you see this, it's kind of strange. Do you know why? There is no penalization part. So, and why it's possible, I mean, to not consider the penalization part. We see that for this case, if the xi the follow the multivariate beta distribution, we don't need regularization. And this minimization problem is converted to a minimization problem over R of the power. This is the dimension of our projective spaces. So it is just, and we use the ordinary least squares algorithm to find the solution of this minimization problem. And the solution is just given by this formula, where this function, this matrix, well, is invertible with high probability. And it's just given by, it is a random projection matrix. And you see what's important, that this matrix, what's the order of this matrix? It's just the dimension of our projective space. So it is a kind of has small order independent of the number of n. N can be very big, thousands or millions, but the dimension is relatively small. So this is a kind of dimension reductions. Okay, and well, our basis functions, because we use some theoretical properties of Jacobi polynomials, so they have this upper bound. And what's interesting is that we are able to get an estimate of the condition number of our matrix. The condition number is, well, is not that small. What does it mean? The condition number is not small. It means that our algorithm is numerically stable. So we have proved two results. The first result is invertible. It's invertible without penalization. The second result, the condition number is not that small. So the numerical computations are stable. And how we proved this result is just by using the mathematical preliminaries. That's Geschke-Green circle theorem and the theorem about the behavior of the minimum and the largest eigenvalues of Hermitian random matrices. So, well, now the order of convergence. So the first issue is dimension reduction. The second issue, we didn't win yet. We have to prove that this estimators has the optimal convergence rate. And to prove that it has the optimal convergence rate, well, we are going to truncate this estimator. This is the kind of truncation. Say the sine of the estimator's solution of the minimization problem times the minimum of a constant kf and the absolute value of our estimator. That's also, we let pi nm the projection, the orthogonal projection over the subspace Pn, our polynomial subspaces. So in this case, this is the order of convergence. It's kind of messy. Don't worry about this. Yes, the expectation of f, that's the regression function, and that's our estimator. There is, say, 3 terms. And when you develop the risk error, that's the risk error. there is two components. The first one is the variance, the second one is the bias. And the variance, this is the variance, sigma square over n times constant. That's the variance term. And this is the bias term. The bias term is, you have to get an estimate of f minus its projection. That's the bias term. And practically every estimator has, when you look for the risk error, you have these two components. And this one, this is it's very small. So don't worry about this one. So this is the usual way. I mean, if you construct an estimator, you have to get the risk error of the estimator in order to get the order of convergence. So, well, uh, well, well what we can, of course, choose the parameter. What parameter we have? We have the parameter n, m, and so on to get the order of convergence. And this, we have to assume some smoothness assumption about f in order to get the order of convergence. Well, sometimes in real applications, we don't know the probability density of the xi are unknown. So what we do in this case, we have to add a penalization term to our random projection matrix. So that's the usual way, though, in order to get the numerical stability of the estimator. Well, now, as I said, if one would has to prove the optimal convergence rate given by Stone in 1982, you have to get his optimal convergence rate, right? So Stone has a condition, a smooth condition. The function f belongs to Cp, and the base derivative is order continuous. So here we assume that the regression function belongs to Sobolev space, periodic Sobolev space. It's equivalent assumption, almost equivalent assumption. And if we assume that the regression function belongs to this Sobolev space, we have a lemma that the expansion coefficient of any, this is a component of the regression function by using the ANOVA decomposition, decays fast. This is the order of the decay of each component from the ANOVA decomposition of our functions. And to prove these results, we have used techniques from approximation theory and Fourier analysis. So why I said, if you want, I mean, to prove that your estimator, theoretically your estimator is good, you have to use tools from other area. So, and sometimes tools comes from Fourier analysis, spatial functions, harmonic analysis, spectral theory, and so on. But don't worry, you can learn these techniques, these tools very fast. I mean, just as I said, I'm using also tools from mathematics statistics, and I didn't study mathematics statistics when I was a PhD or master students. So just tools that one can learn fast and use them. That's it. I talk to young people. Okay. So, and this, in this case, we have this bound of error. And this is useful to estimate the bias term. And in this case, we have the choice now how to find the parameter, the right order of the parameter n, the highest degree of the polynomial, and this is parameter m, the interaction, the maximum number of interaction between variables. And if we choose this is the way we choose them, what we get? We get an order of convergence for the n of the power minus 2s plus 2d minus 2m over 2s plus 2d minus m. That's the order of convergence of our estimator. And if m equals d, we'll get what? We'll get order n minus 2s over 2s plus d. The stone better optimal rate of convergence. But as I said, this is too pessimistic. In real life application, no. We have better results, numerical results. But this is theoretical. That's theoretical. That's the best result one can get theoretically. But hopefully, in practice, this is not the case. Well, now we go to the second kind of estimators, the truncated kernel regression estimators. These estimators, I mean, they are popular now. Actually, the neural network-based estimators looks like a special type of kernel estimator. They are using sigmoid function. The kernel estimator use more general kernels. So, and representative kernel per space is associated with the positive defined kernel. Positive defined kernel, the theory of positive kernel go back to 1950. There is a theorem of Arrangin that says that a positive defined kernel is a reproducible kernel and vice versa. So these are known results from the 50s. And what's interesting that one has 100,000 of kernels. So I cite some kernels, the polynomial kernels. It's just C plus inner product X transpose to Y of the power n. The radial basis function kernel, the Gaussian kernel. This is well used kernel. The Laplace radial basis function kernel also. The sync kernel. This is the nice kernel. The sync kernel, it's a positive defined kernel only for d equals 1 or d equals 3. But I tell you a story. Actually, it is thanks to the sync kernel that I've started working on machine learning 5 years ago. So my main research, as I said, area is harmonic analysis. And with Aline Bonamy in 2009, we started working on estimation of the eigenvalues of the sync kernel operator. So the sync kernel operators, it is a kernel that generates the space of band limiting functions. And this is, the starting point is the sync kernel. The sync kernel. So, and also there is the ANOVA kernel also, but there is plenty of kernels, if not infinite many kernels. Well, why kernel methods can be used at interesting? Actually, there is a representer theorem. Without the representer theorem, these kernels methods cannot be applied. What does it say, the representer theorem? Look at the minimization problem. This is a fairly general minimization problem. Arg mean over the reproducible kernel hyperspace of psi, y1, yi. This is the response variables. fx1, fx2, and f is the regression function. The xi are the random sampling points. And this is the norm of f with respect to the Hilbert space, reproducible kernel Hilbert space. So the solution of this minimization problem is given in a finite dimensional space. This is extremely important result. It means that even the Hilbert space HK is of infinite dimensional space, the solution lies in a finite dimensional space. This is very important. So we have just to get this solution, we have just to estimate this coefficient. This is a very interesting, a powerful theorem, a powerful theorem. Of course, the special cases of this representative theorem have its origin in 1990, in the mid 1990, yeah. But this is the general version. Well, now let's look at the kernel ridge regression estimators. Who is familiar with this estimator, the kernel estimators? Well, so it's just solution of this minimization problem over a reproducible kernel Hilbert space, and the solution is given as linear combination of this kernel. Okay, and if well by order least squares procedure, this is the coefficient, how one get the coefficient. But there's a problem with this formula. The n, the number of observation, can be very large. So the problem is to invert a very large matrix. And this is computational, needs a high load computation, a high computation load. So, but this is useless. Actually, this is really useless. We don't need to invert this large matrix. If, I mean, we know the eigenvalue behavior of gram random matrices. Actually, and this is why the kernel ridge regression estimator requires another n of the power 3 operations. It's too much. And we don't need this high load of computation. So what we do is that we're going to truncate. So how to truncate? Well, we start by a Mercer kernel, and there is also a problem. You have a kernel, say a Gaussian kernel, but you apply this Gaussian kernel to real data, and you don't know the probability density behind the covariates. You don't know. You cannot say that the probability density for lower Gaussian low. No. So we have to assume that the law is unknown. Also, if you use, for example, sync kernel, and the probability density function is Gaussian, the sync kernel, the usual probability density is the uniform density. So how come you use a kernel with random variables that don't follow its usual probability density? So we have this problem, and how to explain this? So we have a partial explanation of this. So the partial explanation of this is that we're going to variable measures. A measure associated with the kernel. What does it mean? Associated with the kernel, that with this measure we do have a behavior. We know the behavior of the eigenvalues, how the eigenvalues decay. And the other is unknown. That's, in practice, this is the case. Well, and now the Bn is the full gram matrix, the large gram matrix, and the An, what we do is just keep the first big N column and remove all the other columns. Small n can be very small. Big N. This can be very small. This one can be very large. And we will prove that our estimator is given as with this form. It was only few coefficient. Just, well, there is some estimators like this, but they don't truncate to the first columns. No, they do single value decompositions or other techniques. We just truncate. And what's interesting is that the coefficients are given by this way, and now this matrix has the small order. It's just an order n, the small n. So it's fast. Well, there is the first such estimator is the random Fourier feature estimators introduced by Rahimi in 2007. It uses this special case of kernel. So, and just this, but what we have done is that any positive defined kernel. So, and let's see how it works. So we have the eigenvalues of our integral operators associated with the usual probability measure. So we have whole informations how this eigenvalue decay, and the eigenvalues of the integral kernel operator with the unknown probability measure. And what's interesting that if we assume that the first operator is 1-to-1 and the unknown probability measure is continuous with respect to the usual probability measure, and by result with Bonamy, we know that the spectrum of the graph matrix is close to the spectrum of the integral operator, and we estimate the error. This is results published in 2020 in Journal for Fourier Analysis and Applications. Also, for example, we give you an example how a usual probability measure is important. For the sync kernel, for example, for the sync kernel, we have shown in the, say, actually, it's a result that to prove it, we had to write 2 papers that how the lambda n behaves. And this is the results. So we spent with Aline Bonamy for 6 years trying to prove this result. And the lambda n, this is the exact super exponential decay rate of the lambda n. Now, with my PhD students, Asma Basaber, we have an estimate of the unknown eigenvalue, the unknown eigenvalues bound for, I know the eigenvalues of the unknown of the integral operator with the unknown probability measure. Also, we have the expectation of the tail of the eigenvalues of the random matrix. And in terms of what? Of the known lambda k. This is important. And we have used it also at realizing inequality of single values and to get also the expectation of this is the single values square of our truncated matrix. And in this case, now this is the risk error of our truncated kernel estimator. So, and if you look at this bound, it's exactly the same order of convergence as the kernel Rittish regression estimator. So, and if we have say if the lambda k decays in exponential way or in way, polynomial way, we have better estimate of the risk error. So this is a theorem that gives us the risk error in these two cases. Well, numerical simulation. So now we are going to apply our estimator to this real life data. Donc, this data is about the quality score of yes, grape. Yes. So the variables we have 1,000 instances. That means that small n is 1,000, and we have 5 variables: x1 cluster weight, x2 berry size, sun exposure, soil moisture, and the rainfall. That's the variables. The response variable is the quality score, and we have applied our kernel by using polynomial kernel with m. That's the higher degree of the polynomial. So our space is just of dimension 1. That's our space, 1 plus 5m. So we're going to truncate to 1 plus 5m, our random matrices, and this is what we get. The penalization parameter is 10 to the power minus 4, and actually, this is the quality score, the mean square error of our estimator. So compare it with the classical estimators like GAM, generalized additive model, or general linear model. It behaves better. And we have just, you see here, it's just 21 coefficient, that's it. So we have inverted 21 by 21 matrix, not 1,000 by 1,000 matrix. So this is coherent with theory. This is what the theory said. Well, now, how much left? 15. Okay. Well, now the third kind of estimator, that's when it's the functional data. Now it's no longer non-parametric regression problem, it's linear functional regression problem. Functional regression problem, think about this. You have a huge data. For example, the data comes from, say, you have many sensors, 100 sensors, and these sensors, for example, collects data, weather data or pollution data, and so on. And it collects this data every hour. And you have the correct data for 1 year. So you have million of of rows of data. And how to deal with these millions of rows of data? So this is typically functional regression problem. So functional regression problem, what does it mean? It means that you don't look at the random variables as random variables, but look them as values of discrete values of a random process. So you don't use random variables, you use random process. So work with curves, not with discrete random variables. That's the idea. So when, and the linear regression function problem is yi, this is the response, and this is the model, alpha 0, plus the integral xis plus times beta 0s. That's the function to find, and this is the noise, the added noise. And the xi, the epsilon I are noise terms, and we assume that the ID-centered real valued random variables with various sigma square, independent of the xi. So the xi are just copies of random process. Random process, a square integrable random process. Are you familiar with the random process? So, and what's an important theorem about square integrable random process is Karoui and Loewe expansion, and the random process can be written in this series expansions, where the phi chi are orthonormal basis. So that's the point. So again, we go back to harmonic analysis stuff. And well, the usual way is, I mean, you centralize the response of the centralized random process, and you solve a simpler linear regression functional regression problem. And well, that's better, and that's numerically more stable. Now, there is many methods to solve linear regression function problem. There's functional principal component analysis based estimator. Also, there is linear functional regression estimator based on kernel methods given by K and Yuan. K, Tony K is here. He's going to give a lecture tomorrow. And what we propose is a random projection based estimator for solving the linear functional regression problem. So this is what Yuan and K proposed in 2010. It's just solve the linear functional regression problem by using the kernel methods over, say, you find the minimization over reproducible kernel Hilbert space. So it's the method that we have described for non-parametric regression can be adapted for linear functional regressions. We're going to use another completely different methods. We're going and what Yuan and K proved that under some condition about the decay of the eigenvalues of the kernel integral operator, and this is the covariance operators. So the kernel-based linear regression functional regression estimators has the prediction error of order. Yes, attains the optimal order convergence error. Sorry. This is the convergence rate of the estimator. So that's optimal. They proved that it's optimal, of course. Well, what we do, we use again the random projection technique to solve the linear function regression problem, and it's the technique is somehow close to the technique we have used for non-parametric regression problems. Just here is the inner product of these are the copies of the random process with the slope functions. That's we are going to do. I mean, we are going to minimize these loss functions. But here, the xi are copies of random process, not random variables. And the solution is this minimization problem can be rewritten as this one. And this one is very close to what one gets for non-parametric problem, regression problem. And well, it's practically the same formula. And now the risk error for the functional regression problem is given by this formula. It's the empirical risk error. And we're going to prove that this empirical risk error is optimal. And this is the result obtained with my PhD students, Asma Sabar. Well, again, there is the bias and the variance term in the risk error. And the variance term includes what? Includes the expectation of this quantity. These quantities, these are the eigenvalues of, yes, single values of random matrix Fnn. And these are the expression of the tail of this sum, the alpha j. These are just coefficient of the random process. That's it. So this is interesting in a way to prove that if we have this bound of the risk error, one can prove that our estimator has the optimum convergence rate too. And we have to assume that the slope function belongs to some Sobolev periodic Sobolev space. And these are the optimum choice of the parameters. There is parameter n, the dimension on which of the projection space, and this is the regression parameter. So if we have this choice of these two parameters, so we get again this order of convergence, n of the power minus 2s plus gamma over 2s plus gamma plus 1. That's again the optimal convergence rate, the same as the one obtained by Yuan and K. Well, now this is in practice. In practice, so these are numerical simulation on real data, Decatur real data. What's Decatur real data? It is generated by near infrared spectroscopy technique. It is a technique, I mean, to get an idea of a chemical component of, say, fruit or meat or other by using beams, say light beams, and these are we can consider this as a random process, copy of random process. So these are actually 50 copy of the random process obtained by the measurement. And well, we have applied our estimator. We have used 167 observation to construct the estimator and 42 observation to test the estimator. And what we get also, we consider the mean square prediction error, the relative or normalized mean square prediction error, as well the mean square error, as well the relative mean square error. And this is the result. You look here, this is once we arrive to 20, and even we consider bigger projection space, the result is the same. This is by theory. You don't need to consider bigger space because there is only 20 eigenvalues, significant eigenvalues. So you don't need more than that. And this is coherent with the theory. I think, well, this is my time is over. So this is some references about this talk. And thank you for your attention.
Thank you. Thank you very much for the very nice report. And any questions?
Thank you for the good talk. So for the example of your first part, could you go to?
Yes,
Yeah, I
yes.
didn't quite understand the results there.
For the non-parametric case,
For the example, yeah,
this one,
yes, yes.
yes,
So here it's from the Kaggle competition, right?
yes,
So you have 1,000 data points,
yeah, okay,
and so your f hat,
yes.
you said it's a error.
Well, actually, yes, the empirical mean squared error associated with the truncated kernel
So
is
empirical mean square. Oh,
yes,
so you only look at the error at the 1,000 data points.
exactly, exactly,
Oh,
because
okay.
we
But,
want, I mean, we have the theoretical results, and we want to see numerically how it behaves. So
but typically we would test on new data, right?
exactly. This is what we have done on the other example, where we have used new data to test.
Right,
It's
but
ju-
here you didn't do that.
yes, yes, of course. It's
You
just
did or you didn't?
I didn't
You
for
didn't. Okay.
the simple reason that we want to exactly see how the theoretical results work in for synthetic examples or real data. So this is the objective. It's not that does it predict well. Yes, the model. It's just
Just the
to
fit,
yes, yes,
just the quality of fitting
exactly,
seems to be quite
exactly,
a bit better. Okay.
exactly. Of
But
course.
you don't know about prediction.
Well, I actually prediction should be of the same type, maybe. But what we have done for the GAM and the GLM, we have used the same procedure, but
Okay.
just to compare with GAM and GLM.
Okay.
So, so, so
So you could have done
of
prediction.
course,
Yeah, could have.
it's nothing. I mean,
Yeah.
yeah, it's
Yeah.
very easy. I mean,
It's easy, but
yeah.
result can be different though.
Well, we yes, little bit different.
Little bit? Are
Little
you?
bit, yes, yes, for
Why?
sure,
Why?
little bit.
Why? Why is that?
Why? Well, of course, because this is
I'm
the
not. I'm not so sure.
that's the theory. Because the theory
The
what
theory.
says what says that you don't need too much information. I mean, to get good results. So, I mean, if you're going to test on a small, let's say small set, you'll get good result too. Does it? I think well, there
Well,
is a small difference, but not that much. I mean, if we
yeah. Well, I don't know. So,
well, well, maybe we may compare with the function regression where we have used both.
okay.
Yes.
Yeah.
For example, here, that's yeah.
Yeah.
Well, this is when we use small set, and here when we use the whole set. So
Okay. You
okay,
compare. Okay.
yes,
Okay. All right. Okay. Thank you.
you're welcome.
Okay, thank you. Thank you, Professor Abderrazek Karoui again. Thank you.
Thank you, thank you, thank you very much.